are you?
I've literally been sitting on that colour on Thursday just trying to make it sound hilarious. Oh, no, it's Ken.
You signed in? Oh, fantastic. All signed in? Brilliant.
I just got charity events, I helped out with them.
You're welcome.
I'm around the charity bucket. In freaking army clothes. It was like, oh, where's your legs?
Still waiting for my response from Dan.
Are you signed in already?
What's the public domain?
Oh yeah, the email.
Yeah, no, I can't risk it. I had just even a screenshot of BBC Outlier. I realised I can't use this, A, because it's not on the website, B, because it's got an image from Italy, and I was like, what am I doing? Sorry. The law doesn't say it works like that, unfortunately. The law is that it's copyrighted unless you get special permission.
If you use the enhanced search on Google, you can the licensing is free to use, change commercially.
I did not know that. I will, thank you. I've got got to work out, I'm going to have a look for an hour and then just finish it as a draft. It's only a draft, so it's not the worst thing. I get some feedback. It's actually good to get feedback about the stuff. Rather than thinking about what is in what we can change. I love how it's critically evaluate. We don't have any words. It's like, no, that's not happening. So I'm just thinking about there's nothing to do.
Good morning.
Yeah, that worked a little bit. Sorry? No, it's just oh, he's live streaming. So it's the live stream. That is. No promises. I think he'll probably swear to be honest with you. Nuts.
We're not meeting anyone. It's like, no, somebody made a roundabouts there.
Good morning.
Ciao.
Good morning.
It's very green.
Yeah, they both. I swear I got it. About 15 tries in total.
I got like 6 or 7.
So what I got 3 and 4 earlier. I understood how to do it. So many times I'm thinking, I've got this, why is it not working? If you're doing this for 80s, surely it should be complementary. And I think they got that wrong because you have to do a complement. It's not going to kneel if it's the same sequence.
You mean for the
Which is only forward. It should be the complementary.
no, that's the thing as well. Because they use RNA, that's why it's so confusing. You would need a complementary, but then they want us to think it's like a common standard RNA or something. So if it goes forward and it could be the exact.
I think you got there. It's like the priming starts from 2' inside prime, and the one that was given to us was 5' and 3', so that we move it to the complementary one. So hence it's just the primer that's provided. That's what the form
Sequence would become 3.5.
yeah. That's how.
I guess that would make some sense. Yeah, that was still really weird. That was confusing.
It is confusing, yeah.
I feel like it shouldn't have been that way because it didn't say specifically it didn't say don't make it complementary. So because it's not there, you don't see it. You can't see something that's not there.
Yeah, that's what I'm saying. It's not a double standard.
That's
I'm seeing right. So every time I'm doing this right. I've got from 39 included 39. It's the right weight. I did the weights and it's like, why is it working? I'm so annoyed.
It's because they want us to see that down. Because you have to go down. You have to think about the direction as well, and then they want us to.
I just think it was a bit silly. I hate that.
Joys of primer design, eh?
Yeah, it was the PCR questionnaire. It took quite a few tries to realise that forward primer wasn't complementary.
If it is any consolation to you, basically anyone who has done PCR work and who had to design primers at one point designed them in exactly the wrong way. So instead of amplifying what you wanted, they amplified the
The
plasma.
rest of it.
Yes. And depending on how experienced you are, it might take you less time or more time to find out that you screwed up.
Don't feel so bad then. Good.
Happens to the best. We've all done it. Right, shall we make a start? Yeah? The sooner we start, the sooner we can go home. Do you have anything after this session? Yeah. Not till 2. Okay, so fair enough. Right, most wonderful good morning, everybody. For those of you where I haven't introduced myself, my name is Peter Klapper, and I have the joy and pleasure, and you have drawn the short straw, of showing you a little bit of data analysis. Because, let's face it, you are scientists, and as such, any claim that you make, and it can be as nonsensical as you like, but it has to be evidenced by data. And you will create the data in your experiments, obviously, but then the big question is, what now? You will find frequently that the data speak a different language to you. So please don't get disheartened if you, for example, ask in the experiment, is it black or white? And the answer from your data is 42. Yeah, happens all the time. Smart people then sit down and think, what the heck is going on? Why are my data saying that? What's going on? And if you then know at least where you have screwed up, then you can learn from that mistake and hopefully do another experiment that gives you a different answer, hopefully the right one that you're looking for. So that's why you really need to do a little bit of data analysis. As I said last week, we are not going into detail. I will try to do that online. What I want to do with you today is just go through a few concepts which you really need to be quite familiar with. So hopefully it won't take till 12, because otherwise my voice is going and you get bored. So let's see how quickly we get done. So first of all, when we are looking at data or when we are doing experiments, we need to be aware what kind of data we are actually collecting. That's absolutely crucial, because depending on the type of data that we get, we can do different things with it. We can't do all the things with all kinds of data. It needs to be specific. So, for example, data types can be classified basically two ways, or there's an overlap. For data types, for example, you have nominal data, you have ordinal data, you have interval data, and you've got ratio data. These are the typical types of data that you encounter. You can also use data and continuous data. And as I said, depending on what data type you actually collect, it sort of informs what you can do with the data, and I will come back to that in a minute. Nominal data is basically just simply a label. So male, female, dog, cat, parrot, tortoise, whatever. These are labels. They are data, of course, but of course it doesn't make sense, for example, to do data analysis in terms of, oh, let's calculate the mean. What's the mean of male and female? Baby. Don't know. Yeah. So you can't do statistics just with the nominal ones, but what you can do is, for example, you can collect counts. So I can collect counts of people who are male, female, non-binary. I think Facebook has 40 different types of, orientation or what people want to, but for our purpose we just have male, female, non-binary, and I can count. Now these counts, again, they can then influence how I deal with the data. And in this case, counts, frequencies of something, would be classified as discrete data. So nominal data usually, if they are translated into, say, counts or frequencies, that would be classified as discrete data. So you can have 3 males, 2 females, something like that. You can't have 3.58 females. That doesn't make sense. Discrete just means basically integers, whole numbers, and there's nothing in between. So these are discrete data. This is in contrast to continuous data. Continuous data is basically anything that you can measure to an nth degree of precision. So, for example, the metabolite or the concentration of a metabolite in the blood, let's say it's 5.35 milligrams per milliliter or something like that. Or it could be 5.36 or 5.38 or something like that. And if you have a very precise tool to measure it, you can expand the numbers of decimals as much as you like. So these data would be classified as continuous data. Make sense? Yeah? Okay, good. Next one are ordinal data, and this is where you rank data. So you give your data a specific rank, in that you say, for example, this is the best student, this is the not so good student, something like that.
Me.
We don't mention any names here, right? So your data have a certain order, although the difference between the different categories, if you like, is sort of not totally defined. So, for example, you find that very often in what is called Likert type or Likert scale type data, you've all done that when you filled out surveys. So you strongly disagree, you are neutral, you agree, and you strongly agree. These are usually the 5 Likert type scales. So and you can rank it, you can give it a sort of an order. But what is the difference between agree and strongly agree? Is it the same difference between neutral and agree? Is it the same span? We don't know. It really is up in the open. So all you can do with this data is you can rank them, and of course you can count a frequency. So for example, if I survey 40 people, 39 said they strongly disagreed that this was a good lecture, right? And one person maybe just simply said they disagreed that it was a good lecture. So you can, again, collect counts. Now, what are interval data? Well, interval data is, again, you have a rank in your data, but in this case, you know exactly that the interval between the different ranks are well defined and measurable. For example, you can say that a typical interval scale is a temperature scale, temperature Celsius, I should say. You know that the difference between 0 and 10 degrees centigrade is exactly the same as the difference between 90 and 100 degrees centigrade. This is just simply the definition of this scale, where the intervals are all exactly as it should be, right? It's very well defined, the intervals. What the interval data don't have is a defined 0 where there is basically no data. So you can say, whoa, time out, wait a moment. The Celsius temperature scale, it does have a 0. It has 0 degrees Celsius, right? Yes, that's right. But it means the temperature scale, in this case, has, you're asking, does it have a temperature? 0 certainly is a temperature. It does have a temperature. And therefore, the Celsius scale is not classified as what is known as a ratio, scale, a ratio scale, has, again, well-defined interval and a 0 point where there is nothing there of what I would measure. So, if I want to measure temperature, I would move away from the Celsius scale, I would move to the Kelvin scale. Because temperature is defined as basically degree of movement of things. So at 0 degrees centigrade, which is just, if you think about it, a totally arbitrary number. Why should we use 0 as when water freezes? We could have chosen 0 as, you know, a temperature when a sheep feels the cold. It's a totally arbitrary number. However, when you look at Kelvin, Kelvin means there is no movement, end of. There is no temperature, if you like, if you define temperature as a degree of movement. So that is basically a typical ratio. It needs to have well-defined intervals, and it needs to have a total, if you like, an absolute 0, where there is nothing there. And how we treat data, again, depends on how we classify these data. So that's quite an important message. Happy with that? Good. We will come to some examples. Right, so that's the data types. Then we need to talk a little bit about almost philosophy. Sample versus population. Now, let me start it this way. You're scientists, right? Tell me, why do you do an experiment? What's the point of doing an experiment? To create a hypothesis. No, that's not why you do an experiment. Sorry?
To test the hypothesis?
To test a hypothesis. Potentially, yes.
To test the hypothesis that we can then apply on the whole population.
I quite like that idea. Let me put it this way. If you do an experiment today or tomorrow or in the lab, wherever, this experiment gives you data, right? You collect some data. And if you think about it, these data are utterly and totally irrelevant. It does not matter what you get. The data are linked to this particular experiment. Well, let me put it this way. I measure the height of 10 people in this room. Who cares? Right? Who gives in the words of the Commons speaker, John Burko, who gives a flying flamingo about the data? Nobody. You have data, you've measured it correctly, so what? But if you think, and exactly what you said, what you think is you are not totally interested, but we come back to that, you are not terribly interested in these particular data. You, in most cases, want to make a prediction about the general height of people in the UK, for example. Now, of course, it would be impractical to measure everybody, and therefore, we use samples. Every single experiment that you carry out is nothing else but a sample. It's a sample of all the experiments under the same conditions that you or somebody else could have performed in the universe and beyond that. Yeah? So if you just measure somebody or something, this is one sample, and a sample has a number of observations, or it can have just simply one observation, a number 1. Yeah? So it's important to realize that whatever I do, it is only a sample. And this sample, which gives me data, allows me then to make a prediction of something bigger. So for example, when you do your CRISPR experiment, in this particular case, you do it just to see, does it work? How does it work? What do I need to do to make it work? But it is just a sample. You hopefully will get some colonies on your plates that are mutants. And what you can say is, okay, I collect data for these colonies. So I've got 115 mutants out of 400 colonies in total. This gives you one specific data point. This specific data point is related to this particular experiment, to this particular sample. But what you want to do then is you want to tell somebody, oh, wow, CRISPR works. The evidence is that in this particular sample experiment, I measured this, and I conclude that for a whole population, if I use all the experiments that I could potentially do, I will get this result. So the sample allows us to make a prediction for a wider population. Samples, and we can talk a little bit about how we get samples. We can, for example, illustrate that by saying that is the entire population of something. And we take a sample of that. And we hope that the sample is representative of this particular population. So, for example, if I say I want to measure the height of everybody in the UK, it's impractical to measure everybody, so I just simply take a sample of people and measure them. Now, if I am unlucky and by sort of coincidence, I just simply measure the height of a basketball team, then it's quite likely that it's not necessarily a totally representative sample of the entire population. So we need to make sure that our samples are representative of the population. Usually, experimentally, this is not a terribly difficult issue because the experiment gives you what it gives you. Yeah? This is more an issue in social sciences or when you do surveys, you know. Even with the best surveys in the world, there's always the danger that it might not be totally representative. So, for example, surveys are quite often are done by phone. Somebody phones you, says, "Can I ask you about, you know, what you watched last night on telly," or something like that. But again, there is a sort of a bias because you will only talk to people who have a telephone where the telephone number is registered. Yeah? So as soon as you do some samples, there is a danger that it does not totally reflect the entire population. Just a little bit of sort of terminology. When we talk about populations, a population is defined by its parameters. So, for example, you can calculate the population mean as a parameter. And it's quite nice to remember which one is which, because population parameter, both start with a P. And population parameters are usually abbreviated with Greek letters. So, for example, the average of a population would be the mean, that's the average, and that is abbreviated with the letter mu. That doesn't mean, in this case, micro, it means just simply population mean. In contrast to that, a sample is defined by its statistics. And again, conveniently, you have an S in sample and a statistics. And statistics are usually abbreviated with just normal letters, just proving, just totally contradicting myself in the case of the mean. The mean for a statistic is abbreviated with the letter X with a line on top. And you read that as X bar. That means that's the average of the statistics. Make sense? It's just simply convention. So next time you hear, oh, I tried to figure out the parameter, you know that that person, if they have a little bit of understanding of population. Yeah? Okay. Now, whenever we talk about populations, we need to be aware of one big problem. And that is whatever we do in terms of statistics, this is a problem that we have. For example, I want to figure out, okay, let's do it this way. I want to know how tall the population is of students who attend the 836 workshop in statistics. Right? For one reason. Don't know why I would want to know that, but I want to measure that. That's my population. You are the population. You are the people. Right? You are the population. That is all I have. And because I'm a lazy person, I can say, right, instead of measuring everybody from this population, and instead of measuring the population mean, I just measure 4 people, randomly selected. 1, 2, 3, 4, right? Totally random selected. I could have said, for example, 1, 2, 3, 4. Do you see a problem with that? There's a bias. I picked the person who is sitting at the edge of the row. So it could very well be that they are sitting there for a reason, because they have got very long legs. Yeah? They are very tall. So I introduce what is called a bias. But just by going randomly, I could randomly assign you a number and then pull that number out of the head, out of a hat. Yeah? That's actually frequently done. So I measure 4 people. What will I get on average? This or this? X bar. Of course, I get X bar. I get a sample mean. Great. And then I think, well, Let's repeat that. So I take my hat with the numbers, pick another 4 numbers, measure another 4 people. Will this sample mean, let's call it x bar 1, of 4 people, will this sample mean be the same, exactly the same as the sample mean from the second round? Sorry?
Most likely not.
Most likely not. Why not? Because I've chosen different subjects, right? So did I make a mistake here?
Wrong sample size?
Wrong sample size? No. It's
Take more samples.
okay. I do another 4 people. I get x bar 3. Will that be the same as one of the others? X bar 1, x bar 2. Will that be the same? No. What do I do wrong?
Nothing.
Nothing.
It's just how it is.
Ah, it's how it is. Now, statisticians have a word for it, for the how it is. What I get here, so certainly x bar 1, or most likely x bar 1 is not the same as x bar 2, is not the same as x bar 3, is not the same as x bar 4, and so on and so forth. They are all different because there is a variability in it who I choose in my sample. Yeah? This is called sampling error. I have sampling error. And in a way, people think, oh my God, error. No, error is not good. Yeah? I must have done something wrong. No, I haven't done anything wrong. As you say, it is what it is. Yeah? Sampling error occurs every time you use a sample. Now, I would like to say sampling error is a little bit like herpes. You do it, sampling, and you've got it. Is there anything you can avoid it? Not a chance. You have sampling error. Full stop. End of. There's nothing you can do about it. Of course, what I could do is, instead of just picking 4 people, I could pick 43 out of 44 participants. Yeah? So my sampling size, and sample size is usually abbreviated with a lowercase n. My sample size compared to the population is very large. But then the question is, if I can measure 43 people, surely I could measure the remaining one, the 44th, and I would not have to worry about sampling error because I can measure the whole population. And the population I can measure with absolute certainty. I can measure all of you, and I get a mu, a sample mean, a population mean, that is absolutely defined. With the sample means, I always have sampling error. There's nothing I can do about it. Are you happy about that? Yeah? So be aware. Whenever you do an experiment, for example, you count the cells on your plates. This is a sample. You could have done the experiment at another time, or at the same time, under exactly what you think the same conditions. You get probably a different count. Did you do anything wrong? No, it is down to sampling error. Actually, it's quite nice because if you think about it, if you do an experiment several times and you always get the same result, it could either mean that everything is absolutely 100% reproducible, or it could mean there's something dodgy. And it turned out, I don't know if you have seen that, there has been recently a report about one of the founders of genetics, Gregor Mendel, who did his pea counts in the garden in Brünn in Austria. And people, and based on that we did Mendelian genetics. That's what we got from that. It looks like that his counts that he did, the sampling error was so small that people think now there was something a little bit dodgy going on. So probably he developed a sort of an idea and then did what people generally call as creative data management. Right? Oh, there are 50 green round peas. I would actually expect 55. Oops, the pen slipped. Right? So it was 54. It doesn't look too suspicious. There's a slide. Yeah? So if there's no sampling error, it's a little bit like somebody without herpes. Don't trust them. Yeah? Sampling error is a must. You can't do without sampling error. And I think that is really what I want you to bear in mind. If you, for example, oh, here's another one. You do a correlation plot. For example, microgram protein versus absorbance. Or microgram DNA versus absorbance. You get a sort of a more or less straight line for that. Fantastic. But don't forget, this is only a sample. You could potentially repeat that. You might get another straight line, which might look like that. Did you do anything wrong? Probably not. It is just simply, this is the sample. This is the sampling error. And we will discuss how you're actually going to deal with something like that in one of the video tutorials that I'm going to send you. Okay, so we've talked about samples, we've talked about population, and this leads us to another point when it comes to samples and population. What do you do? What do you want to do with your data? Coming back to what I mentioned first, what do you want to do with your data? Usually you've got two choices. Either you want to just simply compare the data with themselves. Or I like to call it compare data internally. So you do measurements. For example, very famous experiment is when you have coursework to do, you feel the need to weigh the cat. It's absolutely essential. Yeah? This is a very famous procrastination technique. My deadline is tomorrow, but I need to make sure that the cat hasn't put on any weight. Right? So I weigh the cat. 10 minutes later, you've written one word for your essay. Actually, I wonder whether the cat has put on weight in the last 10 minutes. Yeah? So you keep weighing the cat. Really important. Is this some data that you want to report to the world, or where you want to do any extrapolation to a larger population? Probably not. Who cares what the cat weighs? Probably the cat cares, because the cat is overweight, you won't give it any food for a while, which is, of course, a disaster for the cat. You probably care. Maybe your supervisor cares because you don't get your work done on time, but otherwise nobody cares. Let's say you weigh the cat and the cat weighs 2.0 kilograms. That's at 10 o'clock. At 10 past 10, the cat weighs 5 kilograms. And at 20 past 10, the cat weighs 8.0 kilograms. That's one species of a cat, right? Probably doesn't have any stripes on it. It's not classified as a tiger. What do you think of these data? If I told you that this is the weight of a cat that you measured from 10 o'clock to 10:20, what would your interpretation be? Probably, well, there could be something fundamentally wrong with the cat. Yeah? I fully agree. Or what else? The scales. Or it could be something fundamentally wrong with the scales, with your tool, or with the procedure that you're using, right? So, what you're doing here in this case, you're looking at your data and you compare them with each other internally. You don't make any inference to, well, what is the weight of a healthy cat? You don't make that inference. You just simply use these data internally and compare them with each other. In this case, you would say, wow, there is something a bit fishy going on, something not right. What you do actually here is you use the data, and you use all of the data, and this data is not a sample. You use it as a population. And if you use your data just for this purpose, to compare your data internally, this procedure is called, you measure the precision of the data. That's the precision of the data. In social sciences, this is also referred to as internal validity. It basically tries to answer the question, are the data consistent with each other? So, another person weighs the cat, and they find at 10 o'clock 5.2 kilograms. At 10 past 10, they find 4.8 kilograms. And at 20 past 10, they find 5.0 kilograms. Which measurement is more precise? Which is more sort of internally valid? Of course, you would say this one here. So what you can do actually by comparing these measurements is you can say, well, one of these things is more sort of has a higher precision. Who would you trust for future cut weighing experiments? The one who got the large numbers, or one who got these numbers, or one who got these numbers, left or right? Of course, the right. Yeah, you trust them more because the internal validity is higher. It looks better. The data are less spread out. Does that make sense? Brilliant. So what we have seen is there is this precision there, and you can use the data just simply to make a judgment. For example, is my method all right? Not so much is the cut all right, but is the measurement all right? Is my tools are my tools all right? Is my procedure all right? Yeah. This is what you get with the precision. We used to do a little experiment with final year project students and master students in the lab. We just gave them simply the task to pipette some water into Eppendorf tubes and then weigh the tubes. And from these data, we did not want to do anything else with the data, but we wanted to see how close together are the measurements that the students produced. And with that, we could immediately see, ooh, there is a problem. If the data are terribly spread out, then either the pipette is screwed or the student doesn't know exactly how to use a pipette. So in both cases, we took action and made sure that we could address the problem. Now that, of course, brings us to the other point. We can compare the data externally and we can say, actually, we know that a healthy cat should weigh around 5 kilos plus or minus half a kilo or something like that. Yeah? It's definitely not one of our cats because our cats are hopelessly overweight, but that's a different story. So now we can compare these data to an external reference. And of course, you might have guessed it, this is also called external validity. And I can say, right, okay, good, external validity, I compare it to what I know. So for example, healthy cat is 5.0 kilogram plus minus half a kilo. I'm not a cat specialist, so please forgive me if the true population mean of all healthy cats is not in this captured by this. Now I can say, right, let's compare our cat, the data from our cat, with this external reference. Let's see if there is something dodgy going on. In this case, we will probably argue that for both types of measurements, they are pretty much consistent with this external reference. So I honestly don't really need to worry about it. How we are going to do this comparison, we will discuss. I just want to show you the difference between internal and external validity of data, so that you see what's the difference. External validity is also sometimes referred to as accuracy. So, how accurate are my data means how do my data an external point of reference? Where do they sit? And of course, for that, you need to have an external reference point. Where you get it from, well, that's a different story. Now, of course, we want to describe data in a certain way. Now, for the 3 cut weighing data, it's not terribly difficult to summarize the data. Actually, you would not need to summarize data because you just simply tell your supervisor, I didn't do the assignment, but I tell you, my cat actually weighed 5.2, 4.8, and 5.0 kilograms. Of course, your supervisor will be absolutely ecstatic with this knowledge, because that is what he always wanted to know about the cat, about your cat, weighing on a particular day, measured with these bathroom scales, with this particular method. It's fantastic. Great news. Not. So for 3 data points, we usually don't really have to worry about summarizing data. But imagine you don't have 3 data points, you have 3,000. Of course, you don't want to list them all, because somebody looking at the data loses the will to live. So you want to summarize the data. And for that, the typical measures are the measures of central tendency, which usually includes the average. So what's the average weight of 50 cats? So that's the average, or the other word for that is mean, of course. And we already discussed that. We need to distinguish between 2 different kinds. One case, the population mean, and the other one is a sample mean. Luckily, in this case, there's no difference. The mean is just simply the sum of all the observations, and I write it like that, the sum of all the observations from I equals 1 to n. So this basically means observation 1 plus observation 2. Very often they are abbreviated with a lowercase x. Plus observation 3 plus, and so on, observation n at the end. That's basically this shorthand sum. And what you frequently will find is that people just simply abbreviate it as with the sum sign, xi. They don't bother about the I equals 0 and n and things like that. Divided by your sample size. So if I've got 50 cats, I sum up all the weights and divide it by 50. That is my sample mean, and that is the same as the population mean. Okay? Means are a little bit tricky to handle, because imagine you weigh your cat 5.0, 5.5 and 6 kilograms. That's all right. Yeah. And you do another cut, and you do another cut. Or these are different cuts. Let's say these are different cuts, and you do another cut, and that is 5,500 kilograms. Obviously, you would immediately see, ooh, wow, this is a bit on the heavy side, a bit comfy. Definitely to the vet, because there is something fundamentally wrong. But if you think about it, if we wanted to calculate the mean from that, this mean would be heavily influenced by this last number here, by this 5,500 kilograms, right? So the arithmetic mean, and I should say this equation is the arithmetic mean, there are other means. This arithmetic mean is incredibly sensitive to outliers. If you've got something that is really weird, probably it was just a slip of the pen, and instead of 5,500, it should be 5.5, but actually this is what is being recorded. So in this case, we get a mean that is way out. It's probably in the range of, the mean in this case would be around over 1,000 kilos. 1,200 kilos, the mean, right? Surely that's not right. What you do with that, that's a different story. I just want to illustrate that the mean here is very sensitive to outliers. If you've got something like that, you can deal with it. Instead of the mean, you can calculate the median. And in the median, by the way, what kind of data do we have here? What do you think? Nominal? Ordinal? Ratio? Or interval? Interval? Can we, sorry? They are, first of all, continuous or discrete? They are continuous, exactly, because I can do 5.125 or something like that. Okay, are they nominal? No, probably not.
Ordinal?
Are they ordinal? Is there a ranking in it? First, the heaviest weight, second heaviest? Not exactly. Are they interval? Is the difference between 5.0 and 5.5, is it the same as 5.5 to 6? Yes, so it's interval. Is it, on this scale, is it possible that there's a 0, which means no weight whatsoever, whether a cat is present or not?
No.
Sorry?
No, because you normally get a cat always not.
Whether a cat is present or not, would it be possible on a weight scale to be 0? No weight. Okay, so in this case, we have interval and we have a proper 0, so this is a ratio data. Yeah? And for the sort of statistical Puritans, you can only calculate a mean with either ratio or interval data. Now, in a case like that, what you can do is, however, you transform the data into a rank. So you transform the ratio data into an ordinal number system where you rank the data. And which way you rank them doesn't really matter. you can rank them. For example, you give the 5.0, the lightest one, rank 1, rank 2, rank 3, rank 4. And for the median, what you do is then you order the ranks. In this case, they are already in a nice order, in ascending order, 1, 2, 3, 4, but frequently you just have your data all over the place. So you need to rank them, 1, 2, 3, first rank. You order them, and then you take the middle rank. Let me do another one here. So that would be rank 5. And in this case, for the median, you take the middle rank. And I've done the wrong thing here, so I would need to rearrange my ranks. Let's do 6.1 kilograms. Makes it easier. So 5 is my first rank, 5.2 is second rank, third rank, 6.1 is the fourth rank, 5,500 is the fifth rank. I order them, and then I take the middle. So I need to order them. 5, 5.5, 6, 6.1, 5,500. And from this, I take the middle number here, and that would be 6.0. This would give me the median of the data. Is the median sensitive to an outlier?
Yes.
Yes, is it? If you look at it, here with the mean, we said we get a massive mean, in this case, of 1,000 kilograms. In this case, the median, we get a median of 6.0, which is really not terribly affected by the outlier because we just sort of remove the outlier like that, because we are just going for the middle number in this case. So in this case, I would disagree with you. The median is not very sensitive to any outliers. Makes life a lot easier. On the other hand, you traded the sort of the presence of an outlier and a sort of something that you can deal with easily. You traded it against something that you can easily do a lot of calculations with by transforming ratio data, where you can do lots of transformation with, into ordinal data, where there are not that many tools available to do calculations. But in this case, median is not sensitive. What happens if you have only four data? With 5 data, it was easy to pick out the mean. With general, with an odd number of data, it's easy to pick out the mean. What do we do with 4? Absolutely right. We just simply take the average between the left and the right of the middle number. So in this case, it would be 5.75, the median for odd number, for even numbers. Absolutely straightforward. So mean, median. Last one is, or I need to say, this is, as I said, the mean in this case is indeed the arithmetic. There are other means. There's, for example, a geometric mean, which works differently. Some statistical tools rely on the geometric mean, but we don't need to worry too much about that at this point. Last one is the mode, and you've done that. Mode just simply tells you whether there is a most frequent number present. So if you have 5.0, 5.2, 5.3, 5.2, 5.1 kilograms, you just pick the number for the mode that turns up most frequently. It could very well be that you don't have a mode if no number is more than once. In this case, you have 5.2 kilograms. So that would be the mode. You can have, of course, you can have more than one mode. So for example, if you've got another measurement of 5, then you would have two modes, and you would say that your data are bimodal. With 5.0 and 5.2 kilograms. Sounds trivial, however, this is a very important criterion for doing tests later on, because most of the tests that we are going to discuss in the online tutorials are based on a distribution that has only one mode. Or in other words, if you find that your data are bimodal, have basically two peaks if you plot the frequencies, then there is a good indication that you can't use the tests that I will show you. So that's sort of the first hint that things are not exactly quite usable. Make sense? Of course, we don't want to just have a measure of the central tendency, like these means. We also want to give an overview of how far the data are spread out from each other. And that is the measure of dispersion. Measure of dispersion just tells us how far the data are sort of spread out. And coming back to the cat example, a very simple measure of dispersion is just simply the range, where I just report in which range are my data. In the cat example, bless you, in the cat example, the range would be from 5.0 to 5,500 kilograms. A lot of people would say, whoa, that is a massive range for a cat. So, you know, very clearly somebody screwed up big time, and it's not the cat probably. But for certain measurements, for certain experiments, you will find that you have a massive range. For example, drug effects. And I'm not talking about the good stuff. You will find that sometimes drug effects go over 2, 3, maybe even 4 orders of magnitude. So your range would go from, let's say, 1 to 10,000. Can happen. Doesn't mean that something is totally wrong. It just depends on the experiment. So range, yeah, could be all right. Another typical measure of dispersion, which probably most people haven't heard, is you just simply take from each measurement that you have, you take the mean difference and sum them all up. So what you do is and then you divide by the number of observations. Leave a little bit of space between the different terms when you write that down. Now, if you do that, what is the mean difference between the sum of the mean differences, the sum of the differences, I should say, the sum of the differences between my individual observation and the mean. Just tells me how far are the individual data points away from my average. However, if you do it like that, you will find that this will always give you 0 if you do this calculation. Just simply because you have some data that are on the right of the mean, some data are on the left of the mean. And if you sum them all up, you actually get the mean. So in order to avoid that, people calculate the absolute of the data, of the differences. And absolute turns everything into a positive number. This is referred to as the mean of the absolute differences. It's totally mad. You will find that in some journals where they produce a MAD, but it's not very often that this happens, and it's terribly inconvenient because you can't do proper maths. The reason is that the absolute function is a sort of a V-shaped function, and anything that is not linear is just a total pain in the proverbial. So you really want to stay clear of that. So, as I said, the problem is that if you do something like that, you get positive and negative data, or values. And if you add them up, it gives you 0. How can we convert a negative number into a positive number? Squared. So what you do is you basically take x1 minus x bar squared plus x2 minus x bar squared plus x3 minus x bar squared plus, well, last one would be xn minus x bar squared. Right? Happy with that? We can also write this as the sum of xi minus x bar squared. That's the sum. Now, if you do that for a population, you are dealing with all your values. Let's just simply write that for a population. xi minus, what do I need to write? x1 minus x bar? Sorry? It's a population. Minus mu squared. Yeah? And for a population where everything is defined, I just simply can divide by the number of observations, by the number of measurements in the population, divided by n. This actually has a name because it's very common. This is called the population variance. That's the population variance. And as we said, populations are usually indicated with Greek letters. You would abbreviate a population variance with sigma squared. Squared because we just simply have a square in here. So that is the population variance. Problem is why people don't like it. If you think about it, of our cat experiment, what we measured the cats in kilograms. What would be the unit of a variance? Everything has to have a unit.
Kilogram squared.
It would be kilogram squared, exactly, yes? Because you have kilograms for the measurement minus the population mean, kilogram, and you square it, so it would be kilogram squared. But what on earth does that mean, kilogram squared for the variance? Doesn't make really sense. So therefore, people have developed the concept of, you just simply take the square root of the variance, and that is defined as the standard deviation. That's the standard deviation, and that would be, in this case, population standard deviation is simply abbreviated with a sigma. Very easy. What's the unit of the standard deviation? Well, it's the same as the unit of my measurements, and that's far more palatable. What does it tell me? It just simply tells me how far my data are spread out. Yeah, that makes sense? That is what a standard deviation tells you. Now, we are talking about population standard deviation. What about a sample standard deviation? Now, we need to sort of rewind a little bit. Remember, we had the population. And this population has a certain standard deviation. It has a certain variance, this population. Has a certain spread of the data. We have a sample here. Which one has the bigger spread? Which one has the has a wider range of data, the population or the sample? The population. Population has a larger range. Yeah? So there's far more variability in the population. Now, when we use a sample, we always want to make a prediction about the population. But our sample would usually have only a smaller range, yeah? Because it's just a smaller, narrower subset of the population. And we need to, when we use a sample, we usually want to make a guess about the population standard deviation, especially when we don't know the population standard deviation. What people have discovered is that for the sample standard deviation, there are also mathematical reasons for that, or sample variance. So here's the sample variance. This is usually abbreviated as S square. This is defined as xi minus x bar. Now you see x bar, that is the sample, that refers to the sample squared, divided by, now we say it needs to sort of reflect that what we want to get needs to be more diverse, and therefore we divide by something smaller. That gives us our s squared slightly larger. And the equation for that is n minus 1. So if I have a sample with 3 observations, I simply divide, instead by 3, I divide by 2, n minus 1, 3 minus 1. My sample variance gets slightly larger, because I divide by something smaller. And that gives me an estimate for what the population spread should be. That is where this n minus 1 comes from. And usually it works pretty well. And the sample standard deviation, of course, I abbreviate that as STDEV, because that is the Excel function. If you want to use Excel for calculating standard deviations, you would use stdev.s, and that is just simply the square root of your sample variance. Does that make sense? So you can express your variability in your measurements with variance, or more frequently it's done with a standard deviation. You need to be aware of what is it that I want to look at. Is it internal validity? In this case, internal validity means I use my data as a population, so I divide by n. I use a population variance. If I want to make predictions about the bigger picture, then I divide by n minus 1 and use a sample standard deviation or sample variance. There's one more thing. I'm like Steve Jobs, and I'm not going to sell you an iPhone, sell you another concept before we have a little break. Another measure of dispersion is called, lovingly known as SEM. That stands for Standard Error of the Mean. A standard error of the mean only makes sense in case of a sample. So S and S again. And this is defined as SEM equals the sample standard deviation S divided by the square root of the number of observations, square root of n. So S square root n. And you can, of course, you can see, if you want to present your data, you can use different ways. You can, for example, say, okay, I have a sample. The sample mean is x bar plus minus the standard deviation, the sample standard deviation. That gives people a good idea about the variability of your sample. If you want to show your data graphically, you have your data point, and you can show error bars, plus, minus, and each side of the error bar is a standard deviation. Does that make sense? That is how you would indicate what your standard deviation is. Or you would present your data as x bar equals 5.0 kilogram, standard deviation goes from, and that would be square brackets. Oh, I'm sorry, no, wouldn't. I'm talking nonsense. Standard deviation S equals 0.5 kilograms. That is how you would report it. Yeah? People are incredibly creative because sometimes you have massive standard deviations. So you've got your data point here. You have a standard deviation that is humongous, which of course makes people suspicious. If there's a huge variability in your sample, did you do everything right? Did you use the right tools? Huge variability? Were you totally pissed when you measured the data or something like that? So huge standard deviation usually rings alarm bells. There's something not totally kosher. And what people then do is they just simply say, I've heard about SEM, because the standard error of the mean, of course, is smaller because you divide by something, by the sample size. So if you have a sample size of 100, you would divide by factor 10. Hey, cool, I use my SEM, so my error bars are just like that. That looks much better, doesn't it? That now gives the impression that there is hardly any variance in my measurements, so it must be good. Absolutely fantastic. Hey, cool, I can do it. There's nothing wrong in showing the standard error of the mean as an error bar, as long as you declare it. So you have to put in your legend, what the heck is your error bar? Is it the standard deviation? Or is it the standard error of the mean? Or is it something else? Usually people would not put in the variance, bless you, would not put in the variance as an error bar because that's the square of the standard deviation. It would be even, humongous. But you will frequently see either standard error of the mean or standard deviation. If you look critically at journals, if somebody is trying to sell you standard error of the mean as an error bar, they indeed try to sell me something. They want me to believe that their measurements are far more accurate than they actually are. Caught you, you little bastard. Make sense? That was the easy bit. I suggest we have 5-10 minutes break, and after that I show you another way, and then we go into what is generally known as hypothesis testing and comparing data with each other. Okay? See you in 10 minutes. all too easy.
What?
It's all too easy, that stuff, isn't it? You've done all. Yeah. But the problem is that not everybody has done it. So.
Just speaking.
Sorry?
Just speaking to Jeff. He said, I did my undergraduate degree in mathematics.
Did I say anything controversial or totally wrong?
I'm sure he would have noticed if you had.
You would have.
Oh, Jeff.
Jeff, oh. Okay. Would he say anything? Or is it just too polite? He might have said something.
Yeah, I think so. I mean, he's lived in America for a while, you know, they're quite bolshy. You know, if something's not right.
Good.
Unlike me, well, being much more inclined to just be quiet.
Fair enough. Fair enough.
Like one of those self-scared checkouts took some of my money. It's not too bad. I'm not going to change. Did I say anything about it? No.
It's all pretty easy for you. You've done that before.
Okay.
Sorry?
I think it's just the last part, the standard error of name, that was a bit confusing for me.
We will discuss that in a minute. We will build on.
Until then, it was.
Yeah, just revision. I'm sorry if I bored you, but I know that some people haven't done anything like that.
We needed this. Like
Really?
basics.
It's always good to go back to basics.
Oh, you mean the slider?
It was funny, interesting, then it was sort of I was like, oh, I should have took something.
It's all far too easy. I'm sorry, it's just sort of revision to get everybody on the page, on the same page. So.
It's a good revision, because some of them I've already forgotten.
I forgot as well. So
Sorry?
it was a really good revision. Because
Okay.
we like forgot the whole
Yeah.
stuff.
Oh, no, I was just looking at it. Because you know what types of data, I didn't even know that was
I came over after and I was storage. Yeah, I know the link here. Yeah, it was 182.
Yeah, briefly, because
Oh man, yeah, I like money. It's good luck. It's good luck.
Yeah, I sort of sold them to get a little, like, a feel, but I haven't evaluated them before. I'm trying to look charitable.
Okay, nice.
You're right, though. That's my chance.
See, another way. Don't be polite. Just you know, I put the Bitcoin scroll. It's a gypsy deal.
So I'm going to have a look and send it in. See what he says.
Watch the man.
And one immediately considered to call it.
So they utilized it in doing two better things, right? Just like instead of getting angry and stuff, like overanalyzing things. So they diverted it to do something better, something productive. That was really
Does anyone have the sign-in sheet? The sign-in sheets anywhere?
I think it went on just relaxed.
Ah, sign-in sheet. Brilliant. Has everybody signed in?
I was late in the morning, the traffic was
Don't worry.
Can I sign it?
Yeah, please. I assume this is just revision for you. You've done everything.
Yes,
Yeah.
yes, yes. I had bioinformatics and undergrad.
Brilliant.
You can do it.
Thank you. Okay, shall we reconvene, ladies and jelly beans? Can we reconvene, please?
the rest of the ranking.
Okay, so my apologies to all those of you who, for whom this is just old stuff. But I know that some people have not done that, and I wanted to bring everybody on the same page. So just bear with me. If you have done these things, just relax, enjoy, and think of England or any other country. So I just showed you error bars, and in this part of the session I want to go more into what we can do further with samples, because that is what we are dealing all the time with. So let's not forget, what we want to do is we have a sample, and from the statistics of this sample, X bar and sample standard deviation, we want to make an inference towards the larger picture, the population mean from which this sample comes from, and probably the variability, the standard deviation of this population. Now, of course, we can say, I weigh my cat, the sample mean is 5.0 kilograms, the standard deviation is 0.5 kilograms, and now I want to say, what is the population mean? And that is in general known as inferential statistics. What is the population mean? I can now say, right, from my sample, I believe that the population mean is also 5.0 kilogram. That's the only information that I really have. Population mean is 5 kilograms. What do you think if I say the population mean is 5 kilograms? Makes sense, right? It's not too challenging. Okay. Population, my sample is 5.235 kilograms. Bless you. So I would argue that my population mean is also 5.235 kilograms. Does that actually make sense to you? When I say, I believe from my data that the population mean, that on average, every single cat on average weighs 5.235 kilograms. It's a little bit weird, it's strange, it's too accurate, probably. Yeah. It's a little bit like, today it rained. My prediction for tomorrow is it will rain again and it will produce 10.35878 milliliter of rain tomorrow. Because it's a prediction, I can't be that precise, can I? That much on the mark. So therefore, having such an absolute defined value for my prediction usually doesn't make sense. If I have such a value, this is also called a point estimator or a point estimate. It's just one point. But in a way, if you think about it, it's pretty nonsense to have it that on the dot. It would be far better if I just say, right, I measured my cat and I believe the population mean of the cats is, say, 5 kilograms plus minus, let's say, 1 kilogram. So, or in other words, I think a healthy cat is somewhere between, and this is the correct way of writing that, you have a square bracket, the average lies somewhere between 4.0 kilogram and 6.0 kilograms. So in a way, this is a range where I believe that the population mean is located. And as I said, this is a belief. Or, let's say, educated guess. Based on my sample. Now, of course, it depends on how sure do I want to be. How confident do I want to be actually that the population mean is within this range? Do I want to be very confident about this range? Well, I can say, for example, if I want to be extremely confident, I just simply say a healthy cat weighs, or the population mean, healthy cat on average weighs between 0 kilograms and 50,000 kilograms. Somewhere in between, and I'm absolutely almost 100% sure that the true population mean of all the cats, house cats, Felix, is captured in this range. Does it make sense? Is it practical? Probably not. I just as well don't do any prediction. On the other hand, I can say I sort of got a little bit of feeling that the true range is between 5.1 kilograms and 5.4 kilograms. Ooh, that's a very narrow range. Question, will I be right with that? What's the chance of me being right for that? Not very high, right? So very little confident that I get it right. And of course, we can express that in numbers. We can say extremely confident, I would have 100%, almost 100% confidence level. My confidence level is 99.99999%. And usually confidence levels are expressed in percent. So I'm close to 100% confident that the true population mean is somewhere in between 0 and 50,000. Yeah, it's 100%. On the other hand, I'm a little bit confident, so it's probably 2% confidence level. I'm not terribly confident that this narrow range actually captures the true population mean. So, which one? And what you see is, the more confident we want to be, the wider the range. Very confident, large range. Little bit confident, just a narrow range, but probably not right. Or as a colleague of mine once said it, frequently wrong but never in doubt. I think that's a great quote. When we measure these, or when we think about these ranges where we think that the population mean is located, very often we will use a method that applies a 95% confidence level. And you very often see that in papers quoted at a 95% confidence level. Or what you see even more often is where scientists don't like to talk about confidence, they talk about exactly the opposite. That is significance. So we have a significance level. Oh dear. Oh dear, there it goes. Significance level. And this is usually abbreviated with alpha. And alpha and the confidence level always add up to 1. So confidence level plus alpha equals 100%, or is the same as 1. Very often you see in scientific paper, alpha of the analysis was 5%. And that's a very common significance level. Alpha equals 5%. Sometimes you see it as alpha equals 0.05. That means somebody is confident, has a 95% confidence level that they capture the right range. Yeah? Does that make sense? So what is this tool? How do we find this confidence, or how do we find this range? How to find the range? Find range of the true population mean. Of course, we know that it depends on our confidence level. It also makes sense that it depends on how many data I have. If I've got a huge amount of data, then my predictions are probably more accurate than just 2 or 3 measurements. Yeah? Confidence level, number of data, and it also depends on how much the variability of my sample is. And therefore, this range can be expressed as what is called a confidence interval. It's just a range, abbreviated as CI. Please don't write CSI. Students have tried to sell me that. No, it doesn't have anything to do with a crime scene. CI is defined as we take our sample mean plus minus what is called a margin of error. Or also MOE. That's the margin of error. And we can see in this case, the way I've written it here, the confidence interval is symmetric around our sample mean. So it's margin of error to the left and a margin of error to the right. So it's symmetric. It doesn't always have to be. There are cases where it's different. I'm just playing with words here, right? Confidence interval, margin of error. What the heck is this margin of error? For Christ's sake, tell us. Well, in a particular case here, and I'll come back to that case, you find that for this particular case, the margin of error is x bar plus minus sort of a fudge factor. It's not called a fudge factor, it's an adjustment factor which is also very often referred as the critical t-value. A critical t-value times the standard deviation divided by the square root of n. Wait a moment. Haven't you seen that before? S divided by square root of n. What was that? That's the standard error of the mean. So x bar plus minus t crit times standard error of the mean. So here we actually have our standard deviation from the sample, our sample size. All we need to do is, as I said, we need to factor in our confidence level. And actually, this is hidden in this critical factor here. This includes the, for example, 95% confidence level. Or, if you like, 5% alpha. Now, when does this equation that gives us a tool to make an educated guess where the population mean is located, when does this particular equation work? This particular equation only works when our population shows a normal distribution. What on earth does that mean? A normal distribution, and you find normal distributions very, very frequently. A normal distribution has a typical shape. It's a symmetric bell shape. It is centered around the population mean, and just that. Other criteria are that for a normal distribution, if you have if you measure standard deviations, the spreads of the population, you have one standard deviation, second standard deviation, third standard deviation, and here the same. Each one represents a standard deviation. Characteristic for the normal distribution is that 68% of all your data lie within one standard deviation, left and right from the mean. So that's 68%. The equation for this curve is a little bit more complex, and you really don't need that. As long as you know that 68% of the data are within one standard deviation, and within two standard deviations, that's this orange bit here, you have 95% of your data. That is the typical normal distribution, and that is how a normal distribution more or less is defined. 95% of your data are within 2 standard deviations. And of course, you can do all sorts of weird and wonderful things. So you can ask, for example, how much of my data is larger than 50%? Well, anything that is larger than the mean, because the whole thing is symmetric, 50% is smaller than the mean, 50% is larger than the mean. You can do all sorts of weird and wonderful things. However, this confidence interval, x bar plus minus t crit times s over square root n, strictly speaking, is only valid for this normal distribution. If your population is a normally distributed. Of course, we don't know whether our population has a normal distribution. We just measure a sample, so how would we know? How many modes does a normal distribution have? 1. So if your sample has 2 modes, or if you think there is my population is bimodal, then you know immediately, ooh, I can't really deal with that, with this confidence interval. Very often, what we do is, if we want to use this equation to define the range where we think our population mean is located, we test for normality. I mean, everybody should test for normality. Right. In these crazy times, what is normal? Well, there is a definition, and your population actually should show the criteria for a normal distribution. There are some tests out there to check whether the population has a normal distribution. I'm not going into that in detail. I'll send you a link how you can do normal testing. Does that make sense so far? Yeah? Brilliant. What else have we got? Yeah. Okay, so we have we can define a confidence interval. Every single sample, and that's quite important, every single sample that you take, you can define a confidence interval. So, for example, you measure the metabolite in the blood. You take 15 samples. I always would do something where the calculation is easy. So, for example, 16 samples, because then you've got square root 16, which is 4, which is much easier to handle than 15. And you define a confidence interval. So here is my confidence interval, normal distribution. We believe here is your sample mean, and we think that is also, here that's the confidence interval, say 95% confidence interval. And we believe that somewhere in there is the population mean. Somewhere. Do we know exactly where? No, we don't have a clue. We just believe that it's somewhere in here. Now, somebody else might say, actually, we have done another experiment with a different tool. And we find, for these measurements, a confidence interval that is here. What you see is that the confidence intervals don't overlap. Right? There's no overlap. So, person 1 says, I believe the population mean is somewhere here. Another person says, my belief is that the population mean is somewhere here. Could it be that they are both right? Or who's lying? Who makes the wrong assumption? Obviously, nobody makes the wrong assumption because it's just what they measure, yeah? Could it be that these two samples were taken from the same population? Is that possible? What do you think? You go, yes?
Yeah, I think they are both from the same samples from the same population, but the different maybe parts of the sample.
So what you're talking about is the herpes?
Maybe when he's talking about herpes.
It's the sampling error. It's an interesting point. Because let's not forget, we are only 95% sure that our population mean is in this range here. There is still a slim chance that the population mean is not in this range. So there's a 5% chance. That it's outside. Now, of course, the pink person makes exactly the same assumption. They are 95% confident that their population mean is in here. And there's a 5% chance that it is not in the range that they claim. Now, what is the chance of having a sample with 5% outside and a second sample with 5% outside at the same time? It's pretty slim. It's 5% of 5%. Ugh. So in this case, the confidence intervals are not overlapping, and I hate to disagree with you. I hate to disagree, but in this case, the most likely conclusion would be these two samples do not come from the same population. Yeah? You might still be right. There is a tiny little chance that they still come from the same population, but it's not terribly likely. Make sense? You don't believe me? You have this look on your face. How would you feel if you have the following scenario? Confidence intervals. Could these two samples that I have, for which I've calculated the confidence interval, could they come from the same population? Pink person says, I believe my population mean is in this pink range. Black person says, I believe my population mean is in this black range. Could it come from the same population? Yeah. Yes. So, could come from same population. does not necessarily mean that it does come from the same population. It could be that there's two populations which are very, very similar, but they are different. So for example, cats and small dogs. I get the weight, 5.5 kilograms. I estimate that an animal is between 4.5 and 6 point something kilograms. So if I weigh it, it's a cat. No, it could be also a small dog. Different population, but I can't discriminate if it's the same population or a different one. But in this case, I can say it could come from the same population. On the other hand, if they are totally not overlapping, then I'm pretty safe in saying, no, they come from two different populations. There's a tiny chance that they indeed do come from the same population, but it's not very likely. What about this one? Oh, bugger it. Right? They are overlapping, but not totally. Do they come from the same or from a different? Different? Same. Ooh. Who thinks it's different? Hands up. 1, 2. Who thinks it's the same? Hands up. Who thinks, I wish he would stop now and I can go home? Right? Actually, from that, we can't tell. There's no chance we can figure it out whether they come from whether they could come or whether they definitely don't come from the same population. No way. So how can we find out? Because very often what you will find is you do measurements. So for example, healthy participants in a study and not so healthy participants, you measure a metabolite, you get your data, and you find exactly this scenario. So how on earth can we, make a decision? Is there a difference? Difference between what? Of course, we know there is a difference between the samples. That's a given. Herpes, right? Sampling error. There will be a difference between the samples. But is this difference then reflected in the population? Is there a difference in the populations? So I can, for example, say, with this one, with the pink one, I get mu1, a population mu1. With this one, I get a population mu2. These are my predictions for the populations, for the underlying populations. I know that the samples are different. I know that X bar 1 and X bar 2 are different. That's a given. Sampling error. Herpes. Can't do anything about it. But are the populations different? So what I can do is I can, what is called, formulate a null hypothesis. I can say, I believe the means of the two underlying populations are the same. If the means are the same, that's just similar to saying, well, it's probably from the same population. Or I can say mu1 equals mu2. Or, why is it called null hypothesis? Because you can also write it as mu1 minus mu2 equals 0. Well, in other words, there is no difference between the population means, and I write it as H null, the null hypothesis. There is no difference between the two population means. And all the differences that I see in the samples are just simply due to sampling error, which I can't avoid. So that is the null hypothesis. Null because the difference is 0. Of course, I can formulate an alternative hypothesis, HI. The alternative hypothesis is just simply the negation of the null, in this case. Mu1 minus mu2 is not equals to 0. Or in other words, the alternative hypothesis says there are differences between the two populations, and therefore we have different populations. Does that make sense to you? Yeah? This is also called NHT, which stands for null hypothesis testing. But we now need to identify a way how we can how can we measure these hypotheses. The null hypothesis, there's no difference between the population means, which means it could potentially come from the same sample, from the same population. There's only one population. And we just simply take two samples from it. Or the alternative hypothesis, where we say there are two populations and our two samples are from the different populations. How can we measure that? Well, we can give it a probability. We can give it a likelihood. I should say probability, because likelihood is a slightly different thing. We can actually say, if we could find a sort of a test criterion, we could compare this test criterion with some known data. And from this, we then just simply say, right, it is very likely that our null hypothesis is true, or it is unlikely that our null hypothesis is true. And of course, we want to be, in a way, we want to have a certain confidence in it. Again, here comes the word confidence, or the opposite, significance. We want to make sure that we are most of the time right in our predictions. Again, we very often do a specific significance level, alpha. We want to say, we want to be fairly sure that we go for H null, that we have one and the same population. As I said, we can't rule out it's two populations, but then they are very, very similar. Again, very often this alpha is set to 5%. And this is actually what you do before you do an experiment, you write down your null hypothesis and the alternative hypothesis, and you write down how sure you want to be. That is before you do anything. It's a little bit like okay, let's go to a completely different, this time it's not cat, example. Let's go into law. Seamus has been accused of killing his statistics lecturer. Yeah? Seamus is standing trial. What is the underlying assumption in the UK, in England and Wales, where the jury has to decide, or what is the starting assumption in England and Wales with respect to Seamus? Is he guilty or not guilty?
Innocent until proven guilty.
Innocent until proven, right? So, that is the null hypothesis. Seamus is not guilty. That is what the jury will hear. Why did I say England and Wales? Because in Scotland, there's a different system. In England and Wales, you have guilty or not guilty. Only two things. In Scotland, you have a third one, which is?
Not proven.
Not proven guilty, exactly. Basically, it means you bugger are so smart. We know you did it, but we can't prove it. Right? But let's go with England. Right? Because we're in England and the crime potentially happened here. You only have the option of, the jury has only the option of guilty or not guilty. And the jury has to be, what's the phrase? Sure about the verdict. What's the phrase?
It means unanimous. It has to be unanimous.
It has to be unanimous, and they have to be
Evidence beyond reasonable doubt.
beyond reasonable doubt. This is the confidence level beyond reasonable doubt, or the significance. You must not really make a mistake in your judgment. So the jury sets, or the judge sets an alpha 5%. That is, I would say, alpha 5% is a little bit too risky. There might be a risk that you send him down despite him not doing it with 5%. So probably an alpha of 1%. You want to be 99% convinced that you are doing the right thing. So 99% alpha equals 1. And you can set it to whatever you want. So alpha 1, that is the confidence level, and the judge will, or the spokesperson of the jury, will define this confidence level. They have to give a statement, and that is also in the unanimous included. And the null hypothesis is not guilty. And now the jury gathers information, will be given the evidence. And only based on this evidence is the jury allowed to make a judgment. In data analysis, it is exactly the same thing. Right? In data analysis, you set your null hypothesis. It's always the same. mu1 minus mu2 equals 0. There is no difference between the populations. The next thing that you do is you set a confidence level, or an alpha, 5% usually. And then you get a data. You can't do it the other way around. You can't say, well, we saw him doing it. Let's say, oh yes, what do we do with the null? What do we do with alpha? Yeah, that is not allowed. Yeah. Also, you have to make a judgment, and this judgment is either this one, H0, or the opposite. You can't make a judgment of, not sure actually, don't know exactly what it is. It could be H0.5, that doesn't exist. We are not in Scotland. Right? You have to make a judgment. Otherwise, you can't say anything. And it has to be on the basis of the data that you have collected. Very often, you will find people saying, well, the result is actually statistically not significant. What on earth does that mean? It means the likelihood for the probability that we measure, probability, that these two samples are different, that the two populations are different, is either larger or smaller than your alpha. You assign a probability to that. It can be only larger or smaller. What if it is exactly 0.05 or 5%? Well, then usually people err on the side of caution and they say, no, it's not different. Very often people say, and if it is, if P is larger than the set level of judgment, then people say there is a statistically significant, hang on, I did it the wrong way around, thank you. If P is smaller than alpha, statistically significant difference. If P is smaller than alpha, it's statistically significant, and we can say our null hypothesis is not correct. On the other hand, if P is larger than alpha, then we say the result is statistically not significant. Which means it could come from the same population. Maybe not, but there's good reason to say it still could come from the same population. how can you sort of memorize that? You can say, if P is low, lower than alpha, if P is low, H naught must go. If P is high, H naught can't stay. You have to say that with an Australian accent. Do we have any Australians? No? So, P low, H naught go. If the probability is such that we come to the conclusion, Seamus did it, then he will go down. If it is lower than our threshold, where we accept that, yeah, he didn't do it. Yeah, makes sense? This is what's called null hypothesis testing with p-values. And p-values you get simply from the normal distribution. So here you've got your normal distribution. And you basically say, what is the probability that that the data are in this very unlikely range? So for example, if we take we know that, for example, in the 2 sigma range, we've got 95% of the data. So we know that in this range here, there would be 2.5% of the data and 2.5% of the data here. We can say, for example, we want to be 95% confidence. Our alpha is 5%, so that's this range here. What is the probability that we actually get a value that is either this or smaller or larger? In a way, this p-value gives us the probability that our observed result is the same or more extreme than a test value. Where do we find this test value? What is this test? The test value is actually this value here. That's the test value. It's the test value. How do we find that? Just bear with me for 5 more minutes and then you're free to go. This test value is, you can calculate this test value. The t test value is defined as your sample mean minus, or or let's say sample mean 1, minus sample mean 2, that's when we compare two things, divided by the square root of standard of sample variance 1 divided by n1, by the number of observations, plus S2 sample variance over n2. This would be our test value. Have I done it right? Because you've done maths.
Correct.
And we compare this test value, and all of these things we can calculate from our samples. And we can compare that to a critical value, t-crit, and I'll show you in a video how you find that in Excel or with a table. And if your t-test value is, and we just simply take the absolute, is larger than the absolute of the critical test value, then we say it is somewhere here in this unlikely range. If the test value is larger, then the probability is pretty low for the null hypothesis to be true. Whoa, that was a lot to take in today, hey? Don't worry. I've got links to some very good YouTube videos that I want you to watch. Khan Academy is always a good place to look at these things. What I have introduced you to is what is called a t-test. This is one of the most common tests that you will encounter when you analyze your data, but there are also other tests. A t-test is only valid if you think that your population has a normal distribution and if your data are continuous. If your data are not continuous, or if your distribution is not normal, it's abnormal, no, it's not normal, you need to think twice whether you should do a t-test with it. On that note, have a good weekend. 3 hours of statistics. You were good. You were good. All that stuff is recorded, and I will send you the link to the recording. Thank you very much for bearing